I'm going to start by thanking the organizers for putting together this very nice workshop. I want to tell you about an idea I spent the last 1.5 years, or most of my time, on working. It's an alternative idea for the direct detection of dark matter, in particular for WIMP dark matter. And this is work that I've done together with Katie Fries and Pat Stengel, who are in the audience, and some other people. All right. So we heard a nice talk from Elena yesterday about the Xenon project and some basics of direct detection. So let me just start by reminding you of the basic idea behind direct detection. So we have our WIMPs, our dark matter candidate, that come along and fly around in our galaxy. Most of the time, of course, they don't do anything but fly right by us. But every once in a while, they could meet a nucleus, an ordinary atomic nucleus, and give it a tiny kick, right? Now, of course, the challenge in searching for these events in direct detection is that A, this is extremely rare, otherwise we would have long seen it, and B, the energy you give to the nucleus is very tiny, right? So here I show you an optimistic case of a WIMP coming by with 300 kilometers per second as a function of the mass of the target that you hit from 1 to 100 GeV or 200 GeV. And you see this WIMP, so this is a 5 GeV, 50 GeV, etc. WIMP. You would get a tiny energy of 10, if you're really lucky, 100 keV. And this is the most energy you could suck out of a WIMP like this. All right? And of course, I already said, these things are extremely rare. So what you do is the number of recoils, of course, is proportional to how big your target is, how many nuclei you can accumulate to watch, and how long you stare at this, right? So that is basically the challenge, what we're trying to do. You're trying to observe these really rare events by putting together a lot of nuclei, and you look for one of these nuclei getting this tiny kick. Of course, this program has been carried out for something like 3 decades by now. And as most of you know, all we have so far, except for DAMA, that I'm not going to talk about, is upper limits on the cross-section, right? So this is the standard WIMP plot with the WIMP cross-section here on the y-axis and the WIMP mass down here. And in particular, so for WIMPs heavier than 10 GeV or so, the leading experiment is Xenon that Elena talked about yesterday, and it set this very impressive limit of ruling out this tiny cross-section of something like 10 to the minus 46 square centimeter. And for lighter WIMPs, especially if you go sort of in the GeV range, the leading experimental technology is now cryogenic bolometers. So here for heavier WIMPs, the name of the game mostly is to build a bigger, ever bigger detector to increase your exposure. Whereas if you look for lighter WIMPs, the most important figure of merit is that you want to be able to detect the smallest possible recoils. So you have to lower the threshold of your detector to find even tinier recoil energies. All right. So this program has been carried out for 30 years, and it's going strong. As you heard, the Xenon collaboration is currently putting together the Anton detector, and there's a program to go after lighter WIMPs. But we were thinking about, look, so these detectors are becoming ever more expensive to build, and they're also becoming harder and harder to operate. So is there a different thing? Is there something else you could do to go after direct detection? And the crucial point is, in our idea, that instead of putting together billions of nuclei in a laboratory and just making your target ever bigger, but watching them in real time, which you can only do for a few years or so, could you have some form of detector that is maybe much smaller, but has been looking for these WIMP-induced recoils for a really, really long time? And just to motivate you to listen to me for the next 15 minutes or 20 minutes, we've come up with an idea that I'm going to tell you about, and these are different versions of the sensitivity. All these curves are different incarnation of this possible experiment. Here in gray, it's a little hard to see. These are the current exclusion limits, and here for reference is the Xenon neutrino flow. All right. So the basic idea behind our proposal is what's called solid-state track detectors. So here I'm showing you pictures that are photographed in different ways or obtained in different ways of tracks in natural minerals. And these tracks are induced by ions traveling through the material and creating these damage tracks that you can read out in a number of ways. And the main thing I want you to take away from these pictures is what I'm talking about is not some crazy idea, but these tracks exist and they have been measured for a long time. These tracks are somewhat bigger than what we're talking about, so these tracks are made by much more energetic recoils of 100 MeV or so nuclei traveling through these materials. But these damage tracks exist and can be read out. So these are pictures that you could take in the 60s. Nowadays, with modern translucent electron microscopy, one can take much nicer pictures of these tracks, in particular much more high-resolution pictures. So here you can see some of the details of these tracks. So these are ion tracks going in, the material out, and this is a track going through like this. So what these people have done is they shot ions at a crystal prepared in the lab and then imaged the tracks. So here you can see sort of the details. So these tracks have a diameter of a few nanometers, and depending what the material is, typically what you see is a sort of amorphous core where the material is molten and then has frozen again, but hasn't refrozen in this regular crystal lattice you see around here. But you see this amorphous core, and around this amorphous core you see a ring that people interpret as being due to mechanical stress in the material. All right. So how do these tracks come about? The basic idea of the track formation is not understood from first principle. We have some models, 2 of them are here, that explain different parts of how these tracks are formed. But luckily, of course, we can go in the lab and we can check that these tracks exist and they have been observed. So although they're not understood from first principle, these things illustrate some of the pieces and we know they exist. So this thermal spike model, here the idea is that there's the ion going into the crystal lattice. It interacts with the electron clouds of the nuclei and shakes them around. Then these electrons start to interact with all the other electrons and induce just more motion. So these secondary electrons, these people call delta electrons. And in the end, what happens is you build up what they call a thermal spike. So you just deposit heat in the material that melts your material. And when it then cools down again, it doesn't freeze back into the regular crystal lattice, but you get these amorphous cores that you've seen in the previous slide. Another model is called the ion explosion spike model. So here the idea is that the ion travels through the crystal lattice. Again, it interacts with the electron clouds. It pushes all the electrons away. And then when the electrons are gone, then the nuclei suddenly realize, oh, well, we all have some positive charge. That's not good. So there's Coulomb force. The nuclei get repelled from each other, and you create this lasting mechanical stress in the material by pushing all the nuclei away from each other. All right. So that's the basic idea that we want to exploit. It turns out that many natural minerals are good solid-state track detectors. The basic criterion in order for a mineral to be a good track detector is that it must not be a conductor. So it has to be an insulator or a poor semiconductor. And the reason for that you can understand from these ideas about the track formation, that you can imagine if the conductivity of the material is too high, you push the electrons away, or you move the nuclei around, and everything just quickly settles back and nothing lasting happens. So you need to be a poor conductor. And then the nice feature about these tracks is that once you create a track in a mineral, and if you don't do something very crazy to the mineral, these tracks are going to preserve in many materials for timescales that are much, much longer than the age of the Earth. There are some minerals where at room temperature, these tracks would persist for something like 10 to the 60 years. And luckily also, nature has provided us with a source of very old minerals that have been sitting around and could have recorded these damage tracks that come from WIMPs coming by and interacting with the nuclei. So Earth is something like 4.5 billion years old. It took a while for Earth to cool down, etc., and create quite enough environments. But the oldest minerals that are found on Earth are something like 2.5 billion years old. And there are many minerals available on Earth that have been sitting around for 1 billion years in quiet environments. So that's the basic idea that we're trying to exploit. Use an old mineral that has been sitting around on Earth for 1 billion years or so, and in that mineral, look for these tracks that could have been induced by dark matter. And the basic idea why it works is that time is enormously powerful. So if you can imagine that you can read out 100 grams of target material that has been recording WIMP events for something like 1 billion years, if you want to match that exposure with a conventional direct detection experiment that you can maybe run for 10 years, you would have to operate a 10 to the 4 ton detector, which I think nobody is really dreaming of building a 10 to the 4 ton xenon detector. All right, so let me tell you a little more about So we're not the first ones to think of this idea. So a similar search has been carried out in the mid-90s by Dan Sloan-Ift and collaborators. They did set a limit, so they used ancient phlogopite mica, which is a well-known naturally occurring mineral, They picked it up from the Smithsonian, to everything I understand, just here. They went there and asked, hey, what is the oldest mineral you have? And they got a piece of mica, and they looked for it in the tracks. They did set a limit, but if you look at the numbers, of course, it's not very impressive. It's 10 to the minus 31 square centimeters, which is something like 16 orders of magnitude worse than the best limits we have nowadays. So the reason why we think that it's worth to revisit this approach and to try it again is mostly that modern technology to read out this track now should allow to do this much, much better and to reach a competitive sensitivity, whereas back in the 90s, the technology to read out these nanometer scale features just wasn't good enough to make this approach competitive. All right, so let me tell you a little more about the details of how this works. So the new piece, if you want to think about what does the dark matter signal look like now, is you have to calculate, of course, for us the observable, you have to calculate the track length spectrum and not anymore the recoil energy spectrum, right? So you all know how to calculate the recoil energy spectrum. It's in every dark matter paper. So the new piece is now to convert this to a track length spectrum. So the stopping of ions in the material will be due to electronic stopping and nuclear stopping. And it's been shown that both of these pieces do lead to track formation. So we don't have to care about to tell these two pieces apart, but we can just sum it up. So what you do is you just calculate the stopping power for the ions and you integrate it to get the track length. So here I show you in some material, it doesn't matter. These curves look very similar in a wide range of materials. The track lengths here on the y-axis from 0.1 nanometer to 10 to the 4 nanometers versus the recoil energy. And you see, unless you have some very light nucleus like hydrogen, the curves look all rather similar. And the second nice piece you can read off from these tracks now, from this plot now, is you can guesstimate what would your threshold be. So imagine you have a way to read out your material where the shortest tracks you can read out are something like 1 nanometer long. So you see if you have 1 nanometer, this corresponds to a recoil of something like 100 EV or a little less than that. So that would be a recoil energy threshold that's comparable to what you can achieve in cryogenic bolometers. Whereas if you would have a readout technology that allows you to have a resolution of something like 10 nanometers maybe, you would get a threshold of a few keV, 1 or 2 keV. So then you would run an experiment that would be much more similar to something like xenon. Of course, dark matter is not the only thing that can make these tracks. So the name of the game here is the same name of the game as what you play in a conventional direct detection experiment. You have to understand it, you have to control your backgrounds. So of course the price we have to pay for getting this enormous exposures, we're not anymore running a lab experiment where we can't necessarily control the backgrounds, but we're picking up a mineral from somewhere in nature that just has the backgrounds it is. So we worked a lot on trying to understand the backgrounds that are there. So the first thing you might think about are natural defects occurring in the mineral, right? We're talking about just picking up something. We're not preparing the mineral, but nature has made it for us. Now, luckily, it turns out after we talk to people that understand how minerals grow and form, that natural defects look nothing like these tracks that dark matter could induce. So natural defects in minerals are always either single-sized, so there's one atom missing in a lattice, or they stretch across the whole monocrystalline domain. So they're either much smaller or much larger than the tracks we're interested in. So we don't have to worry about natural defects. And I should say the answer from the mineralogist about this, when we asked him about this, was not, this is what normally happens, but every once in a while, it's just very rare, but you could get something that looks like what you are interested in. But the answer was, this is the only thing that happens, and there's no way how a natural defect could look like what you're interested in. All right. The next background, of course, is cosmogenics. So you have cosmic rays raining down on Earth, right? And they can either make, if they're charged, they can make a track themselves, or they could interact with the nuclei in your target material, give them a recoil, which then gives you the track. And the basic approach is to do the same as what you do in a conventional direct detection experiment. You go deep underground to be shielded from the cosmic rays. Now, the advantage for us, of course, is we're not talking about running a ton-scale experiment in a laboratory where you have to get the people into it, you have to drive a truck into there to build the experiment, etc. But we're talking about getting a small amount of material from somewhere in the Earth. And if you're interested in getting a small amount of material, you can get that from much, much deeper in the Earth than the few kilometers of overburden that you can achieve in a conventional direct detection laboratory. So in particular, what we've been thinking about is you could use boreholes. So geologists and people that are searching for oil drill these boreholes quite routinely. the deepest ones are something like 12 kilometers deep. And when you drill these boreholes, you pull out a bore core that is something like a meter or so in length and has a diameter like this of a decimeter or a little more like this. And in these boreholes, there's plenty of material. There's many kilograms of materials in a single bore core. So this would be one idea how you could get a mineral from very deep down underground. And if you could go to a depth of something like 5 or 6 kilometers or so, then all the cosmogenically induced backgrounds will be essentially negligible compared to the other backgrounds I will show you. Okay. So then the next problem, of course, is radioactivity. And the first thing you do is something very similar to what you do in a conventional direct detection experiment. So there, of course, you choose your materials very carefully to build your detector out of radio-pure materials. Now, we don't have this option. Instead, we can go and we can just pick up material that is radio-pure. So if you would pick up an average mineral that forms in the crust of the Earth, the radiogenic backgrounds in that would be prohibitively high, and they would ruin your sensitivity to any interesting dark matter parameter space. So instead, what we propose is you could use either material that is formed from the Earth mantle material. So for example, you could have some lava being transported up to some kilometers underground, and then they're cooling down and forming materials. And the reason why this works is that the mantle is much more radio pure than the Earth's crust. So it's a few orders of magnitude more radio pure, and then you could achieve interesting sensitivity. The other option that we've been thinking about is what's called marine evaporites. So these are minerals that form at the bottom of an evaporating ocean out of the salt that is falling out at the bottom of the ocean. And they are extremely radio pure. And the reason for that is mainly that seawater is just one of the most radio pure substances that exists on Earth. So the most worrying radiogenic background that I want to tell you a little about, of course, is neutrons. Because the problem with neutrons is they're very similar. What they do is very similar to what dark matter would do, right? They're neutral particles that would travel through your material, and the way they dominantly lose their energy is by elastically scattering off the nuclei and giving rise to backgrounds. So, of course, we have to, as I already said, we have to get a clean material, but then we have to calculate and understand our backgrounds in order to understand our sensitivity. And there's two important sources for radiogenic neutrons that we include in our background modeling. So one of them is spontaneous fission. So every once in a while, right, your uranium atom will just undergo fission and not the usual alpha decay. And the fission event itself is not a problem. So you get these two heavy nuclei that go away with energies of 100 MeV or so. They make these big, beautiful tracks that I showed you in the beginning. They're orders of magnitude longer than the tracks that dark matter could induce. So you don't have to worry about the fission event itself, but you also get two neutrons with MeV or so of energies that give rise to backgrounds. And the second source is what's called alpha N reactions. So there's a lot of alpha decays in your material. We don't worry too much about the alpha decays themselves, but every once in a while, there's a rare process where the alpha particles could hit a nuclei, and this nucleus would then spit out a neutron that could give rise to background events. All right. And finally, of course, there's neutrinos, and there's nothing you can do about neutrinos, right? So you just have to live with them, and you just put them in your background modeling. So this is then how this would look in the end. So here I'm showing you the track length spectrum as a function of the length of the tracks from 1 nanometer up to 1,000 nanometers. So this turquoise line you see here is what's induced by the neutrinos. So you see it's mostly important. It's the dominant background at small track length. And this greenish line you see going down here is what is induced by all the radiogenic neutrons in your material recoiling off your other nuclei. And here I show you some signal spectra. So this is a 5 GeV WIM, 50 GeV WIM, and a 500 GeV WIM. So you can imagine if you look for lightish dark matter, 5 GeV or something like that, below 10 GeV or so, the dominant background is going to come from the neutrinos. And here in particular, this piece are the solar neutrinos. Only over here you would have atmospheric neutrinos. Whereas if you look for heavier dark matter, then the limiting background is going to come from the radiogenic neutrons. All right, how could you go and read out these tracks? So I'm briefly going to tell you about two ideas. So one of them is X-ray microscopy, and a particular version of it where you go to a synchrotron and you use the nice hard X-ray beam that is produced by the synchrotron, and you do essentially computer tomography. So you focus the beam on your sample, you get a diffraction image, you scan the beam over your sample, and you piece together all of these diffraction images to get a 2D picture, and then you rotate your sample and play the game all over again. just as you do in a computer tomography if you go to the hospital, and you build up a 3D picture of your sample. So what's been demonstrated with this technology is that you can read out samples, bulk samples that can be quite large, with a spectral resolution of something like 50 nanometers in 3D. So this would be one way, and we think with this you could read out realistically something like roughly 100 grams of target material within a year or so. Another idea what you could do is if you want to have better spatial resolution is you could use helium ion beam microscopy, which is a technology that's been developed in the last decade or so, and now you can just go and you can buy one of these. It's a tabletop size machine you can put in a lab somewhere. So what you do is it has a helium ion beam, a low energy helium ion beam that you shoot at your target, and you measure the back reflected either the helium ions, or you could also measure secondary electrons that are emitted when the helium ions hit the target, and that allows you sub-nanometer resolution. So I think the best resolution that's been demonstrated with this 0.3 nanometer, and again, you can do 3D reconstruction of a sample with this. So here I'm showing you a picture of a rodent kidney, and one of the nice things about this picture here, the scale bar is 5 microns, and down here it's 50 nanometers. So it's a zoomable technology where you can choose how big of a sample do I want to look at, and what does my resolution have to be? Of course, the better resolution, the smaller the sample you can look at is, but it's a zoomable technology, which is very nice. So you can imagine you can identify some interesting region of a crystal and then scan that quicker, scan it with higher resolution. Now the downside of this, of course, is whereas here with the X-ray microscopy we thought you could do something like 100 grams, here, a realistic benchmark is rather something like 10 milligrams or so of target material you could read out with a track length resolution on the order of nanometers. So let me show you what you can do with this. So this is a version of the plot that I showed you in the beginning, just with a few, not as many minerals on there. So I'm showing you two incarnations of the experiment. One is what we call the high resolution configuration, so this would be the realization with the helium ion beam microscopy, where we think you should be able to achieve something like a nanometer spatial resolution, and you could read out something like 10 milligrams of target material. So of course, because of the spatial resolution, which if you remember in the beginning I told you correlates to having a very low threshold, this is mostly geared towards low mass dark matter. So here you see the sensitivity in a few different target materials. So it reaches essentially down to the neutrino floor. Of course, now you have to recalculate the neutrino floor for this particular target, etc. But we could achieve sensitivity that are many orders of magnitude lower than what is currently being probed. So the current limits are somewhere far up here. And in a different incarnation of the experiment, if you would use the X-ray microscopy readout, say you could achieve a spatial resolution of something like 50 nanometers, but you could read out a much bigger target of something like 100 grams, we believe. And then, so this is a little hard to see, but these are the current limits in this gray area. They sit somewhere here, just above this white line. And if you have a good target material, here the most promising is epsomite, which is a marine evaporite that forms at the bottom of the evaporating oceans. You could achieve a sensitivity that is 1 or 2 orders of magnitude below the current limits. So that's on the level of what you can do with xenon and ton, or LZ. And I should also say that this doesn't necessarily have to be the best sensitivity you could ever reach with this. So imagine the situation of direct detection, right? When people started with this 30 years ago, if somebody would have told you could achieve the sensitivity that xenon has today, probably everybody would have laughed about you. So in the interest of time, I'm going to skip about an extra piece that we've recently looked at. Come and talk to me if you're interested in it. So we just put out the paper. You could not only look for dark matter with our Paleo-Detectors, but we've shown that we think it's a promising method to, for example, measure neutrinos from core collapse supernova, and that would allow you to get a direct measurement for the first time of the core collapse supernova rate in our galaxy, which is very important because the core collapse supernova rate, for example, is directly proportional, or thought to be directly proportional to star formation rates. You could understand, you would get a direct measurement of the star formation history of the universe going something, of our galaxy going something like 1 billion years back. All right, so let me end with this picture that Quantum Magazine chose to put on top of an article about this idea. I'm not quite sure what this pink smoke is supposed to be, but it's a nice picture. Thank you.
Okay, questions? Yeah.
So I would like to ask if you can say more about the possibility to observe cork-collapsed supernova neutrinos, and I also have a question related to that. In that paper, you mentioned that one of the challenges is related to data acquisition and storage. And I was wondering whether that is also the issue for the application to direct detection searches or not.
Okay, so let me start with the second part of your question. So if you imagine you read out 10 milligrams of target material with 1 nanometer spatial resolution in 3D, that's a tremendous amount of data if you just naively would think about it as a picture you have to store. So there has to be, you have to come up with a smart way how to deal with the data if one would run this experiment. Luckily, in the experimental community, of course, there's a lot of experience in dealing with large data sets and analyzing them. So we're not too worried about this as of now, but it's something that we have to deal with before running an actual experiment. Of course, you don't have to actually store all of these pixels, right? But you can compress the data a lot because you're actually interested in the damage feature. And if you want to read out the data, right, so what you're doing is literally pattern recognition, right? You're trying to find a track in a picture. So it's an ideal application for machine learning, which one of the things that it's best at is pattern recognition, right? So we think that would be the way to deal with the data. So to talk about supernova neutrinos, so the basic idea is, right, cork-collapsed supernovae are the supernova that make a lot of neutrinos. And neutrinos give rise to nuclear recoils, similar to the way that dark matter does by elastically scattering. So this is coherent elastic scattering of the nuclei in your target, right? So whereas for dark matter, the neutrinos are, of course, a background, you could also understand them as a signal. Now, in a conventional direct detection experiment, we normally don't talk about neutrinos from the cork-collapsed supernovae in our galaxy, because most of the time there's no supernova going off. Of course, if there would be a supernova going off, then there would be a nice signal, and one would certainly look for it in a direct detection experiment also. But now we have an exposure that is on order of 1 billion years or so. So people think the cork-collapsed supernova rate, it's never been directly measured in our galaxy, but people believe it to be on the order of 2 or 3 per century. So if you measure for a time that it's long compared to 30 years or so, you would just integrate over the cork-collapsed supernova rate. So for the people that know about the diffuse supernova background direct detection experiment, the flux from the cork-collapsed supernova in our galaxy, if you integrate it over time, over a timescale that's long compared to the inverse rate, is a factor of roughly 100 larger than what you get from the diffuse supernova, which are the supernova that go off all over the cosmos. So we could measure these supernovae, and by measuring the normalization of the spectrum, right, you get a measurement of the supernova rate, which, as I said, we have no direct measurement of this. So that would be very interesting. And what you can then also imagine, of course, if you look at a particular target, you don't have any timing resolution, because these tracks don't come with a date stamp, right? But what you could do is you could imagine, let's look at, instead of looking at one sample, let's look at, say, 10 samples, where one of them is 100 million years old, the next one 200 million years old, etc. So by measuring the integrated rate after different times, of course, then you can take the derivative and get a handle on the time dependence of the actual rate. So that's what I'm showing in this plot here. So here we took 2 benchmarks for what people believe the star formation rate to evolve. So here the blue points are what the cosmological star formation rate is. So if you would just say the supernova rate in the Milky Way scales like the cosmological star formation rate, that would be very hard to disentangle from just a flat from just a time constant supernova rate. But there's some measurement from recent Gaia data that points to the star formation rate 1 billion years ago being a factor of 2.5 or so higher than today. And if that would be the case, we think you could get a sort of 5 sigma detection to prefer a time evolution like this in Paleo-Detectors compared to prefer this kind of time evolution over a time constant supernova rate.
So 2 questions. One on your supernova rate measurements. If you have sources that are distributed in a disk, so
Yes.
that the flux goes RdR, and you're measuring integrated rate, which goes as 1 over R squared, I think you'll find that the variance is dominated by the nearest source. So if you go to compute your error rates, you'll have a very hard time measuring integrated flux from within our galaxy. So I suspect the error bars you find are kind of unbounded, right? You have these large non-Gaussian tails in your errors when you try to do rates that way. So I'm concerned about that and wondered what you thought about that. My second question is, in a sense, related to this for dark matter. I understand for an underground experiment, when they see something, how we could be convinced that they're seeing something real. On the other hand, if you saw excess flux or excess event rates, I think we would not be able to conclude from that we've learned something about dark matter. So it seems like this might be a very interesting way to get limits, which is valuable, but not a route to satisfying the NSF requirement of detection while the NSF director's alive.
All right, so let me start with the supernova question. So I think the crucial point here is that the time scales one would integrate over are enormous, right? So if you integrate over hundreds of millions of years, you get a lot of supernova in this time. So we did specifically look at how close would an individual supernova have to be to dominate the spectrum, and it would have to go off within something like 10 parsecs or so of the Earth. So you would have to have an extremely nearby supernova. Now you can turn this on the hat, and you can ask for, by looking for differently aged samples, you can try to look for such an event, for one very close by supernova going off, right? Of course, that's degenerate with having something like a starburst going off in the galaxy, but you can turn it on the hat and you can use that. But so as I said, in order for one individual close by supernova to dominate the spectrum, if you're talking about integrating over something like 100 million years, it really has to be within 10 parsecs or so of us. Okay, so the other part of your question, can you ever see something? So of course, as you say, so it is if you naively think about it, it's an exclusion machine, and that works nicely, but we think you could actually make a detection. So first of all, the way you would analyze the data is very, very different from how you think about normal direct detection experiment, right? So in a normal direct detection experiment, you're trying to essentially arrive at a background-free experiment, and you then look for a few events, a handful of events, right? And you do a counting experiment. Whereas here, there would be a lot of background experiments, a lot of background events, and if there's something to see, we're not talking about seeing 5 or 10 events from induced by dark matter, but depending on the mass, where you look at thousands to tens of thousands of events. So the way the analysis works now is not like in a normal direct detection experiment, but it's much more similar to something you would do, for example, at LHC. So we do have energy resolution through the track length. So you have spectral information. You know the shape of your background spectra that you can calculate, and you can test them in the lab from radioactivity and from neutrinos, etc. And you can calculate what the spectrum from dark matter should look like. And you can use, for example, what you can do is you could use, if you look at the spectrum here, you can use control regions. So for example, if you go to very long track length, then the radiogenic neutrons, this background is going to dominate. You can use the long track lengths to normalize the background and use it as a control region to learn about the background in your signal region. So you could play these kind of games. And because we do have spectral resolution, and because as I said, we would see a lot of events, you could check, does the signal spectrum that you observe, does it have the right shape? Does it behave like what dark matter should do? And of course, that's not going to convince anybody. But what you do then, okay, you go to a different target, right? A target composed of different different target nuclei. And you check, right, do I find the same spectrum here? Does the signal scale correctly with whatever the interaction is that you think it is, right? Say if it's canonical, spin independent, does it scale with A square, etc.? Does the signal scale correctly with the age of the mineral? So there's a lot of games you could play to convince yourself if you see something that you actually have observed a WIMP.
Okay, thanks. Let's switch talks, and we can take one more question while we're setting up the next talk.
I'd like to comment on the supernova rate. For some other reason, I happen to have just a few days ago calculated the number of supernovae you'd expect within a kiloparsec in the last 20,000 years. And so I know that number, it's 5. And and if I now scale it, you expect around 5 in 100 million years, within 10 parsecs. So that seems like David's point is a very painful one for you.
So the supernova rate, of course, it's not homogeneous through the galaxy, right? So what people, as far as I understand, what people believe is that the supernova rate essentially follows the disk density.
That's what I calculated the usual model of supernova sources.
Right. So it's dominated, if you think about the rate integrated over long times, it's dominated by a distance that's roughly at the galactic center. The flux is dominated by 8 kilopascals. Right, okay, yes. So if you count them within 10 parsecs, I think you would expect, I can look up the number, but I think you would, we calculate this, you would expect like, you know, there's like a 10% chance that within a billion years there would be a supernova within 10 parsecs. 10 parsecs is very close.
My number is different from that number.
I'm happy to look at it and discuss it.
Okay, we're going to move on. Thank you very much. Our next